Oh, that was fun. So what do we have it tonight? Paella, or is that turkey chili? Or Hi, Sachari, how you doing? Sachari,
Yes,
how are you doing?
I'm doing well.
Doing fine. Is there something I can help you with?
No, sorry, I was just logging in early just to be in.
No problem. In that case, I'll go back to my wonder word puzzle.
Okay, no problem.
You're okay with everything?
Yes, Professor, I'm fine.
All right, good enough. Found another word. Jana? Jana? Are you hearing me, Jana? Jana, are you hearing me? Nope. Ethan Araceli, are you hearing me?
Yep.
Yes.
Okay. Hard essay quiz, huh?
Well, it certainly took me a while to answer some of them.
Yeah. Yeah. I need to fix question number 10 though. It's under there as a multiple choice test, a quiz, and
Yeah, I
that needs to be
noticed.
fixed. Got one more pop quiz.
Wait, would that mean I would need to redo the pop quiz? Because like I did the version of like when like the
No, if you look, Ethan, you got a 10 on it.
okay.
I graded most of them on Sunday. I think there was only one more person that submitted something on the 5th, but they're graded. Actually, I could go in there and see.
I think I didn't realize until like later that it was actually due in like
It doesn't
18th.
matter. Ethan, if you check the actual until date. I think I have it set for the 20th of July. Yeah, I did that on purpose. Yeah, it's available until July 20th. If you're out there, guys, and you haven't done the pop quiz, please do it before the 20th. And okay, I got some people to do it. Okay. One, two, three, four, 5, 6, 7, 8, 9, 10. I gotta do 10 of them. Okay. And you guys are all wimps. You guys are all wimps. You don't want to go. You don't want to take a chance. $1,000 is nothing, guys.
I mean, well, if you saw my answer, like,
Anybody have anything to question me on?
Did you already go over question 8 by any chance on the
On the
quiz?
quiz? Are we talking the
I just got here. I'm sorry. I don't know if you
I'm
already went over it.
asking, Manuel, we're not talking the post lab. We're not talking about the pop quiz, are we?
No. Those were just no, not at all. No.
Okay. And which quiz number was it?
I think it was 12, the one that was due today.
Okay. Okay. Question 8.
Yeah, the very last one.
Was that, did I have some worth more than 1 point?
I don't know.
Yeah, the last 2 are worth more than 1 point. Okay. All right. Basically, all you have to do for this manual is you have to do Hess's law. Okay. And remember, in Hess's law, it is products minus reactants.
Mhm.
All right. There are 2 NO2s. So my delta S has to be 2 times 240 or 480, a negative 4. That's just equal. That's a positive 480, right?
For delta S or delta H?
I gotta see how this is written. I can't see. Those are all positive numbers. Okay.
Yep.
Delta S's, this is a positive 240 joules per K, and the N2O4 is a positive 304.4. Right?
Well, we need to convert that to kilojoules, right?
Eventually, yes. But for right now, we're not going to worry about it. All right. So you have 2 NO2s. So this is
Okay.
480.2 minus 304.4. So that gives me my delta S is going to be 175.8 joules. Right?
Okay. I don't have a calculator on me, but I'm just
Yeah,
trusting.
I just did it on the calculator.
Okay.
Okay. Now my delta H's. Now, I'm hoping I didn't screw it up, but there's always that possibility.
Well, because
Alright.
I started with delta H because the equation for delta G is delta change in delta G equals change in delta H
that's a
minus
positive.
T minus or times delta S or changing delta S, right? Right? Something like that.
I'm sorry. Manuel, I was just trying to figure out whether I gave you the right numbers, and I did. What was it you were just saying?
That the no, you're good. The delta G equation is change or delta S or delta H minus
T delta
T.
S.
Oh, so we didn't have to factor in temperature in
Yes,
this
you do.
equation?
Yeah, you do. Delta G is equal to delta H minus T delta S.
Okay.
So your delta H is going to be 33.2 times 2, or 66.4 minus the 11.1.
Yep. And then minus
So that
the
is a positive 40. I got a positive 55.3 for that. That's my delta H.
okay.
My T is going to be 298 because it's in Kelvin.
Yep.
So I got 298 times 175.8. That gives me 52,388 joules. I've got to divide that by 1,000 because I got to relate that to kilojoules. That's 52.3, 52.4 kilojoules. So my
Wait,
delta,
but I'm sorry. Are you dividing the previous answer by, because we're still working on delta H, right? We haven't figured out
Oh,
delta S, or did you already do delta S?
all right, let's do it one step at a time.
Okay.
My delta H is going to be 2 times a positive 33.2
Uh-huh.
minus 1 times 11.1.
Yep.
So that gives me a delta H of a positive 55.3 kilojoules.
Yep. Okay,
All
I
right.
got that too.
So I'm going to do my delta S's.
Okay.
2 times 240.1 is 480.2
Okay.
minus a 1 times 304.4. That gives me 175.8.
Uh-huh.
And
Joules.
and because it's T delta S, I have to multiply that 175.8 joules per Kelvin by 298 Kelvin.
Yep.
And I do that and I get a number of 52,388.
Okay.
The 52,388 though is joules. So I have to multiply that by 1 kilojoule over 1,000 joules to get 53.4 kilojoules.
Okay.
Then simply it's going to be
Subtraction.
55.3 minus the 53.4. That should be a positive 1.9.
Okay. Yeah. I put all that in my calculator. I got like a negative 129. So I must have done something wrong.
Yeah. And yeah,
Yeah,
I
because
got
what
the
I
correct answer here is 2.9.
okay. Yeah. I had originally like started off converting joules to kilojoule. And then yeah.
You can do that. If you do that, you just get 0.1758 kilojoules that you have to multiply by 298.
It gets everywhere. Unfortunately, stuck in my pants being a frequent malfunction. I'd be pulling a 3-foot hair out of my pants after making sure no one is around.
Somebody that is dealing with hair and pants needs to.
Turning around when you realize you've gone the wrong way or forgot something.
My daily routine is easy.
Guys, thank you. Thank you. Manuel, you good?
Yeah, I'm good. Thank you.
All right. Anybody else have any other questions, quiz or otherwise? How did you do on these thinking questions? Like which has the most entropy? Like which of the molecules has the most entropy? Did you do okay on those?
Oh, I had a question about the ones where you gave us the answer options as aqueous. I didn't understand why it was the answer it was.
These ones?
Yep.
Okay, which ones has the most particles?
Well, I picked NaC2H3O2.
This has 5 particles though.
No, oh, okay.
You see the subscript 3 under BA and 2 under PO3? That has 5
Okay.
particles. That should be the correct answer.
Can you please go through question 7?
Okay. All right. All right, we got to look at this. We got to look at what we are dealing with. First compound is iron 3 oxide. Is my equation in the right direction?
Yes.
It's not in the right direction because in my equation with the delta G, my Fe2O3 is in the product side. In the reaction I want to determine delta G, it's on the reactant side. So I have to flip this reaction. So now after I flip this reaction, this becomes a positive 742.2 kilojoules. Then I have to look, is my second equation in the right direction? Do I have a CO on the reactant side? Who's asking the question? Is it
Yes.
Ether?
Mm-hmm.
Ether.
Yes.
Is this, I have my first reaction, I had to flip to get the Fe2O3 on the reactant side, which meant that I had to change this from a negative 74.2 to a positive 742.2.
Okay.
I look at my second reaction, 3 COs. Are the COs on the right side of the reactant side?
It's right?
They're both on the reactant side, but I have 3 in my reaction. I only have 1 in my smaller reaction. So I have to multiply the bottom reaction here by 3.
Mm-hmm.
If I do that, I get 3 COs plus 3 halves O2 yield CO2. So when I add, remember I have flipped this reaction. When I add these 2 reactions together, I get the top reaction. So at that point, all I have to do is add these up. And I have 257.2 times 3. That's a negative 771.6. Minus a negative 742.2. That gives me 29.4. That's my final answer.
Okay. Thank you, sir.
Anything else, ladies and gentlemen, before we start off today? We good? We good? All right. I'm going to stop share here and pull up the PowerPoint. We are going to finish. We're going to finish chapter 18 today. This is the chapter on entropy. On Thursday, we are going to do most of electrochemistry. We're going to finish that up next Tuesday. and we are going to start nuclear chemistry next Tuesday. That will get finished up by next Thursday, and that's everything. We have a test, let's see, today is the 6th. We have a test on the 20th. Our final is on the 22nd. The final will be, I'm not going to say. Let's see. Yep, we're here.
Wait, is the final like ACS? Like the
No.
Okay.
You got to thank God it's not. All right. I just want to really quickly look at something. All right. It is not, there is the final right there. It is not multiple choice. There, I believe, are about 6 questions on the final. I will go through and talk about that at a later time. But hold on a second. I got to make sure somebody's not trying to get in.
Did he just say the final is not multiple choice, you guys?
Yeah, he did.
Yeah, and he also said it's like 6 questions. Am I right?
Yeah, what?
I mean, okay.
No, no. Okay. Do we have any questions about the way the last couple lessons line up? Any questions about that? The 20th, we have our 3rd test, and the 22nd is the final. Okay. Having done that, let's get back to where we were and what we were doing. When we ended class on Thursday, are predicting the spontaneity based upon enthalpy, entropy, and temperature. We have to understand that our formula is delta G equals delta H minus T delta S. And you have to realize when we are doing this, what's happening with the individual equations. If I have this expression and my delta H is positive, in other words, my delta H is endothermic. If my entropy, if I am losing entropy, that means my negative T delta S term is also going to be positive because I have a negative multiplied by a negative delta S. If I have a positive delta H and I have a positive T delta S, either is my delta G ever going to be negative?
Yes.
I have a positive delta H and I have, since my delta S is negative, my T delta S term is going to be positive as well. Is there any possibility that delta G can be negative?
No.
So in order for something to be spontaneous, delta G has to be negative. Does this circumstance ever leave itself to a point where it can be spontaneous? If delta G is negative, the reaction is spontaneous. Can this ever be positive or negative? You just said a second ago, Ethar, that delta H, because it was positive, and the T delta S term, because delta S is negative, is also going to be positive. Right, Ether?
Yes.
So can delta G ever be negative?
So delta G will not be negative.
It's not going to ever be negative. So delta G has to be positive. The reaction is never spontaneous. Jana, you had a question. Jana, you were raising your hand.
I'm sorry, I forgot my question. I forgot the question. I'm sorry.
No, that's fine, Jana. Just if you remember it, just feel free. I'm sorry, I was trying to get that point made before I answered your question. I'm sorry for that. If you think of it, just type it up, just yell it out, okay? So under these conditions, under an endothermic reaction where I am losing entropy, my delta G will always be positive, and because delta G will always be positive, it can never be spontaneous. Come on.
Hey, I actually have a question.
I'm here, Manuel.
So like if we're ever looking at a test question, how could we determine that delta G is positive or negative unless
This is
we're
a test
told that?
question.
Okay,
Test
all right.
question. Give me the answer. Endothermic reaction, Manuel. What is the
Okay.
sign of delta H?
Okay, so you have 2 moles of N2O gas minus. No, am I not on the right track?
No, you're not. Let's
Okay.
answer the question I just gave you. Endothermic reaction. What is the sign of delta H?
Oh, positive.
Okay. Now,
Okay.
now look at the reaction.
Okay.
How many particles do I have on the reactant side?
On the reactant side, you have 3.
How many do I have on the product side?
2.
So am I gaining or am I losing entropy?
Gaining or lose? Well, you're going from products minus reactants, right? So that's a negative number.
How many particles do we have on the left?
3.
How many do we have on the right?
2. So we're losing. Yeah, we're definitely losing.
All right, so what's the sign of delta S?
Negative.
You're losing entropy.
Okay, so losing entropy means. Is it negative? I'm sorry, I'm like overthinking this.
Yes, you are. You're overthinking it tremendously, Manuel.
Is it negative though?
It is negative, yeah.
Oh, okay,
because
okay. All right.
your final entropy is less than your original entropy, right?
Okay, yep.
If your final entropy is less than your original entropy, then your delta S is going to be negative. Now, apply it back to the equation. You said delta H, because it was endothermic, is positive, and my T delta S term is going to be negative because entropy, you lost entropy, right?
Yep.
So I got a positive minus a negative. Is delta G ever going to be negative?
I mean, yes, right? From.
I've got a positive delta H. Right, Manuel?
Okay, wait. One question. So like the difference in moles, that's delta S, correct?
Yeah, it depends. In this particular case, we were dealing with all gaseous molecules.
Okay.
If this would have been a liquid plus a liquid making a gas, then I'd have had an increase in entropy.
Increase in entropy. Oh yeah, because
Because we're
it goes
going
from gas,
from a liquid
yeah,
to a gas.
Yep.
But under this circumstance, I'm losing entropy. So if I go back to my delta H minus T delta S, my delta H is endothermic, so it's always going to be positive.
Positive. Okay.
My delta S is negative.
Okay.
So I got a
So
positive
losing.
minus a negative. A positive minus a negative. Is there any possibility that delta G is ever going to be negative?
No.
Since delta G can never be negative, it's non-spontaneous under any condition.
Okay.
Does that make sense, Manuel?
Yep.
And you have to work it through like that,
Okay.
one step at a time. On the other
Wait,
hand,
I'm sorry. Last question. I'll stop talking. Is this like one of the 4 steps that's mentioned in the book? Like where there are different like circumstances of
yeah,
like
I'll
delta
get to that in
H
a
or
second. I think I know.
okay,
what you-
okay.
Wait. I think what you're talking about is this slide, right? That slide?
Well,
Manuel, are you talking about this slide?
yeah. This one. Yep.
All right,
this one.
so yes, I do get to it eventually.
Okay. All right. Thank you.
I'd rather you think through these things though. Okay. Okay. What happens if my delta H is negative and my S is positive? In other words, I have an exothermic reaction and I am gaining entropy. Well, just look at the signs. If H is negative and S is positive, I've got a negative number subtracting a positive number. Can delta G ever be anything that's not negative? Jana? I've got a negative number minus a positive number. Will delta G always be negative?
No, it won't always be negative.
I have a negative. What's a negative minus a positive? Negative minus a positive, Jana.
It's
What
gonna
does
be a
that give you? A positive or a negative number?
Mhm.
Negative minus a positive number.
Negative
Doesn't matter the
number.
quantities.
Negative number.
It's always going to be a negative number. If it's a negative number always, if it's a negative number under all conditions, it's going to be spontaneous. Natalia, you have hexane being combusted with oxygen, making 6 carbon dioxides and 6 waters. Okay, Natalia? It's an exothermic reaction. What is the sign of delta H?
It's gonna be negative.
All right, now you've got 1 liquid and 9 gases, 1 liquid and 9 gaseous molecules making 12 gas molecules.
Mhm.
Is the entropy increasing or decreasing?
Is it increasing?
It's increasing because I'm getting more gas molecules. All right, now I have a negative delta H minus a positive delta S. What is the sign of my delta G going to be under all temperature conditions?
Negative.
So is it going to be spontaneous always?
Yes.
Guys, you should be answering this with the person that I'm putting on the spot. All right, consider another circumstance. If I have my delta H, if I have an endothermic reaction, but I increase the entropy, my delta H is positive minus a positive number. So I've got a positive term and I got a negative term. I got to figure out which quantity is bigger. If my T delta S term is bigger than my delta H term, then I'm going to have a negative delta G. If I have a negative delta G, it's going to be spontaneous. On the other hand, if my delta H is bigger than my T delta S term, my delta G will be positive. If my delta G is positive, it is non-spontaneous. So how do I get my T delta S term to be really big? My delta S is not going to change, but my T can change depending upon the temperature. If I increase the temperature so much that the T delta S overcomes the delta H term, then my delta G is going to be negative. If my delta G is negative, it's going to be spontaneous. So if I have a high temperature with a positive delta S, that will overcome the endothermic delta H. On the other hand, if my temperature is low, then my T delta S term is going to be smaller than my delta H. My delta H minus T delta S will then be a positive number. It's going to be non-spontaneous. Jenna. The dissolution of ammonium chloride is endothermic. What's the sign of my delta H, Jenna?
It's going to be, delta H is going to be positive.
Delta H is going to be positive. Now, I'm taking solid ammonium chloride and I'm dissolving it in water. Does my entropy increase or decrease?
Would increase.
So I've got a positive delta H term and a positive delta S term. Describe conditions in which this is spontaneous. Jenna, what does delta G have to be for it to be spontaneous?
A negative.
Negative. Delta H is positive. My delta S is positive. So is it under high temperatures or low temperatures that my reaction is going to be spontaneous?
High temperatures.
Because at that point, my T delta S is going to be bigger than my delta H term. Since I'm subtracting T delta S, the T delta S, because it is bigger than my H, is going to make a negative delta G. Under high temperatures, this will be spontaneous. Under low temperatures, it will be non-spontaneous. Are we confused? Are we okay, guys? Is this making sense? All right. I have a reaction of nitrogen and hydrogen to ammonia. The reaction is exothermic. Do I gain entropy or do I lose entropy? Is my delta S positive or negative, Emily?
It's negative.
So I've got a negative delta H because it's exothermic, but I also have a negative delta S. So under what conditions will my reaction be spontaneous?
In low temperatures.
Low temperatures. My delta H is negative. Under low temperatures, my T delta S term is going to be real small. So I've got a negative number and I'm subtracting a negative number from it. I want to keep the negative, I want to keep the entropy low. The T delta S term low. I make the T delta S low by making the temperature low. So under those circumstances, my low temperature is spontaneous. Guys, if you don't want to, If you don't want to think through it, memorize the table. Negative delta H, positive delta S, spontaneous, all temperatures. Positive delta H, negative delta S, non-spontaneous, all temperatures. If both the delta H and the delta S are negative, it's going to be spontaneous at low temperatures, non-spontaneous at high temperatures. If both delta H and delta S are positive, it will be spontaneous at high temperatures, non-spontaneous at low temperatures. If you have to memorize it, then go for the memorization. Any questions about these type of problems? I'm trying to stall here so you can write everything you did. Jenny, you good? Anybody else need more time to copy this page down? Okay, I'm going to go on from there. Yep.
You're still on the table, right?
No, I wasn't. I just moved.
Okay, because my screen keeps freezing, so like I'm behind.
All right. It is in the. Dear God, where am I at?
I have the PowerPoint like printed out,
we
so I'm
go.
trying to follow along, but like my screen's frozen on the table and you said you just moved past it, so I can't see what we're doing.
Slide 103.
That's what slide we're on right now?
That's the slide with the table.
Okay.
We good?
I think so.
Who's speaking?
Jordan.
Okay, Jordan. All right. Are you okay, Jordan?
Yeah, I'm just gonna have to listen to it because it's just frozen.
Yeah, I'm sorry, Jordan.
That's okay.
Either that or go through, look at the video later. Maybe that'll help.
Okay.
Okay. Consider the reaction. 8 sulfur trioxides making 1 S8 plus 12 oxygens. Predict the sign of delta S. What do you think? Benita. Guys, I want all
Hello?
videos on. All videos on. I want to make sure you're attending. Benita.
I can't turn my video on. I emailed you today. I'm taking my son to his doctor's appointment.
Okay. I'll let you go then, Benita.
Okay, thank you.
Keanu. Keanu, are you there?
Yeah. Yeah.
Okay. Are you seeing the screen?
Yeah.
All right. What is the sign of delta S? You got 8 gaseous molecules making 1 solid and 12 gaseous molecules. Do you think delta S is going to be positive or negative?
I would say positive.
My delta S is increasing. All right, Keanu, an endothermic reaction. What's the sign of delta S? Or delta H?
Positive.
Positive. So I have a positive subtracting a positive number.
Positive number.
Under what conditions is this going to be spontaneous?
I'm not for sure on that.
High temperature, low temperature. You got a 50-50 here.
High temperature.
If I have a high temperature, Keanu, my T delta S term is going to be big, right?
Yeah.
So if I get the temperature high enough, the T delta S term will be bigger than the delta H. My negative term will overcome my delta H. My delta G will be negative. Therefore, it will be spontaneous under high temperatures. Are you getting this?
Yes.
I have a question.
I'm here.
Why? Because I thought that delta S was gonna be negative because isn't endothermic delta H positive and delta S negative?
No. They're not related. They're
So,
two separate aspects.
so I'm
Delta
having,
H is the enthalpy, delta S is the entropy.
okay, right. So, no, I understand how to identify delta H, but for delta S, how did you say that it was positive in this one?
Okay. How many gaseous molecules do I have on the left?
I have 8.
How many do I have on the right?
For gases, you have 12, but overall is 13.
That solid doesn't matter.
Oh, that's all right because it's solid.
It's
So
a solid. So I'm going from 8 into 12. I'm
So-
making more particles. If I'm making more particles, then I am increasing the entropy.
Right. Okay. Okay.
If I go from a smaller to a bigger, that's also increasing the entropy.
Okay.
All right.
I get it now. So wait, so we're always gonna have to look at the molar ratios.
Kind of, sort of, yeah. You're going to have to look at the number of particles on both sides. All right, who's speaking? Natalie?
Natalia, yeah.
Natalia. Good, Natalia. Look at this equation.
So I would say for delta H is going to be positive,
What's type delta H? What type of reaction?
exothermic.
Exothermic reactions are positive or negative?
Oh, negative because they're releasing. Yeah. And then for delta S is going to be positive because we have 3 particles.
Well, it's not the 3 particles. We're going from a solid to something being dissolved. Aqueous means it's dissolved.
Okay.
So for that reason, are we increasing or decreasing delta S?
Is it decreasing?
Do we have more? Would you say the entropy on the product side is bigger or smaller than the entropy on the reactant side?
I would say it's bigger.
If it's bigger, then final minus initial, is delta S going to be a positive or a negative?
Positive.
So I have in my equation,
Yes.
I have my T delta S. Sorry, I have, where's that? There we go. I have a negative delta H, but my delta S is positive. So my delta H term will always be negative, and my T delta S term, my negative T delta S will always be negative. What is the sign of my delta G always then?
It's going to be negative.
If delta G is negative, is it spontaneous?
Yes.
There we go.
Okay.
Okay. Now, we're going to have to apply some numbers to this. We're going to do some delta G 0. Whenever you have a 0 above a term, that means under standard conditions. So if I want to find the delta G for that reaction at 25C, also 25 degrees Celsius is considered standard conditions. So if I want the delta G of this reaction, I'm going to have to take my sum of my products minus the sum of my reactants. That will give me my delta H value. I'm going to have to sum my products minus sum of my entropy of my reactants. That will give me my delta S value. I then multiply that by 298. So what is my delta S, H? How do I figure out my delta H here? Chari, how do I figure out my delta H here?
It has to do with the molecules, right?
Yep.
So if you have 5 on the left and 4 on the right.
I want the exact, Chari, I have given you values. I've given you values for each of the heats of formation of all the compounds. Do you remember Hess's law, Chari?
Hess's law. Not off the top of my head.
Okay, then I don't know. It's a perfectly good answer. Ethan.
Professor, do you have to multiply the 18.4 times 4?
Yep. All right, who's that? Natalie?
Natalie,
Absolutely.
yeah.
You're going to have to multiply the 18.4 by 4. Then what are you going to do?
You multiply the 102.3 times 1.
And what are you going to do between the two of those?
You're going to subtract those two.
Absolutely. Because what we're doing, we're taking the coefficient, multiplying the coefficient times the heat of formation of each one of the products, summing all those up, adding all those up. Then we're subtracting out the coefficient times the heat of formation of the reactants. So for my delta S's, I'm going to have 4 times a negative 18.4. From that, I am going to subtract 1 times 102.3. I add those up. This is 4 times 18.4 is going to be 73.6. That's a negative 73.6 minus a positive 102.3. This should end up being, this answer should be a little wrong, and it ends up being, should be a positive 28.7. All right. If I give you the delta S's, that was just the delta H's. Jessica, you just saw us do the delta H's.
Mm-hmm.
Can you give me an idea how you're going to do the delta S's? Hess's law doesn't
Would
change.
sulfur be multiplied by 1 and you sum them up, right? Like all of the reactants together.
Well, tell me what to do.
So
remember, it's products minus reactants.
I actually don't know. I'm sorry.
That's fine. Jordan? Are you on the screen, Jordan?
Yeah, I think I'm on the right screen.
The delta S for S2Cl2 is 331.5.
Yes.
That's the screen? Okay. So Jordan,
Okay.
how am I going to find the overall delta S of this reaction?
You're still doing products minus reactants, right?
Tell me how to do it.
Okay. So you do 331.5 times 4.
Okay.
Minus 430.2 plus 223 times 4.
Okay. Something I want to point out to you. Jordan, that was good.
Okay.
Delta H's, pure substance in its natural form, the enthalpy was 0. That is not true for delta S's. So absolutely, I'm going to do all that. And I end up, after I subtract everything out, of a positive 3.8 joules. Remember, that is joules, and the delta H is in kilojoules. Keep that in mind. At that point, I get the negative 28.7 minus my T has got to be in Kelvin. It was 25 degrees centigrade plus 273. I get 298 Kelvin times 3.8 joules per K mole. I need to change my joules to kilojoules, so I'm multiplying that by 1,000. I get negative 28.7 minus 1.1. I get a negative 29.8. How are we doing with this? Does it seem fairly straightforward? All I'm doing is applying Hess's law to my enthalpies. I'm applying Hess's law to my entropies. Then I am plugging it into the delta H minus T delta S formula. Anybody confused? New problem. I want to find my delta G reaction and spontaneity at 1055 K. Strategy, just like the last problem. I'm going to use Hess's law to find delta S. I'm going to use Hess's law to find delta H. Then I'm going to plug it into the formula delta G equals delta H minus T delta S. Those are my delta H's and delta S's. And let me see what I'm doing here. Okay. Okay. Rhea, what are we going to do? We have to find our delta H of reaction, and we have to find our delta S of reaction. Tell me which one you want to do, delta H or delta S.
H.
Okay, tell me what I'm doing.
Are you taking the two, 1,000 to 07.6 and then subtracting?
Remember, Hess's law, I'm taking my products, my sum of my products, and I'm subtracting the sum of my reactants.
Okay.
So tell me what I'm doing.
So you're taking the delta H and then subtracting it by the...
Tell me the numbers, Rhea.
Okay. So 1,207.6 and then minus...
Is that a reactant or is that a product, Rhea?
It's a delta H.
Is it a reactant or is it a product in the reaction?
A product.
CaCO3. The reaction is above you on this screen here. You're saying that CaCO3 is a product.
A reactant.
Thank you. Now, Hess's law says products minus reactants.
Yes.
So what am I doing?
So you're subtracting the
My bad, dude.
other two, the 634.9 and then the 693.5.
693.5, where is that? 393.5.
Sorry.
So I'm adding a negative 634.9 and a negative 393.5.
No, where's the pen? What's the stuff on?
That gives me a negative 1028.4. What am I doing then, Rhea?
Are you gonna do the S now?
Nope, we're doing the delta H. We haven't finished the delta H yet. You told me I add 634.9 and negative 634.9 and a negative 393.5. I added those two together and got a negative 1028.4. What do I do next to get my delta H?
So you subtract that from the 1207.6.
Absolutely. And that gives me my delta H value of a positive 179.2. Okay? Anaya. Rhea has just done the delta H's.
Okay.
I want you to do the delta S's.
Okay, so 38.1, which is CaO, and add it with CO2, which is 213.8, and then you add those and then you subtract it from 91.7.
And I get a value of 160.2 for that. So I got 179.2 kilojoules for delta H. And I got 160.2 joules per K. I've got to change either the kilojoules or the joules. I chose to take my delta S. Manual. Manual.
Yes.
Could you, I believe that's you that's having a conversation. Could you mute yourself, please?
Oh, yeah, sorry.
So I get my delta S is 160.2 joules per K. I multiply that by 1 kilojoule over 1,000 joules. That gives me 0.1602 kilojoules per K. I just simply plug that into my formula. My positive 179.2 kilojoules minus my K times my delta S. I do this math out. I get a positive 12.2 kilojoules. My reaction is not spontaneous. Questions, ladies and gentlemen? This is more a methodical plugging away type of problem. If you get asked it, you got to use Hess's law to figure out what your delta H's are and the delta S's. You're going to have to change either your delta S to kilojoules. Actually, you want to do that. Forget there's not an option here. You need to change your delta S to kilojoules because delta G's are reported in kilojoules. You're going to change your delta S to kilojoules, multiply that by the temperature, and subtract it from the delta H. That will give you your delta G's. Questions on this type of problem, ladies and gentlemen? Another problem. At what temperature is the following reaction spontaneous? Enthalpy is a positive 199.5. The entropy is a positive 476 joules per mole K. Parker, you out there, Parker?
Yeah, I'm here.
Okay, Parker, I take it that you sent me that last page.
I did. I resent it through. I replied it through the email. I was going to resubmit it through the lab page, but it wouldn't let me.
No, I realize that. Don't worry about it. I'll get it and I'll fix it. All right.
Okay.
I just wanted to make sure you sent it. That's all. Parker, we have a problem here.
Yes.
The question is, at what temperature is the following reaction spontaneous? My enthalpy is 199.5. My entropy is 476 joules per mole K. Can you think of a way we can solve this problem?
Could we use the Gibbs free energy formula or no?
Yeah, we can use delta G is equal to delta S minus T delta G is equal to delta H minus T delta S. How do we know a reaction is spontaneous? What are the circumstances? What does delta G have to be in order for the reaction to be spontaneous, Parker? I think you're giving me robotic talk now, Parker. I think we're having problems with the connection. Ethan. Under what conditions?
I do not know.
Under what conditions?
Is it? I know certain ones have to be positive. Or is it?
What are we saying all along? Delta G has to be positive or negative to be spontaneous.
Delta G has to be positive.
What's your second guess? Ethan? What's your second guess?
Well, I guess if it's not delta G has to be positive, then it's like delta G is negative.
Yes. Write this down, ladies and gentlemen. This is an important concept. Delta G is negative under spontaneous reactions. So how are we going to solve this problem? Anybody have any suggestions?
Professor, would you set the equation to 0 and then
Beautiful.
From there subtract, you're gonna take away 199.5 from both sides. We'll move it to the 0 side and then divide by the 0.476.
Absolutely beautiful.
And then solve for the T.
What you're going to do is you know that Gibbs energy being negative is going to be spontaneous. You're just going to set Gibbs energy equal to 0. Then you are going to solve for the temperature. Then any temperature bigger than that amount will make T delta S larger than 199.5. That's the temperature that's going to give you a negative delta G. So let's work through this problem. I'm going to set Gibbs energy equal to 0. My delta S was 476 joules. I have to change that to kilojoules. So it's 0.476 kilojoules per mole K. I set it equal to 0. I get negative 199 is equal to a negative 476 T. My T is equal to 419 K. 419 minus 273, I get 146 C. Now, if my reaction is at 146 Celsius, then my delta G is equal to 0. In order to get my delta G equal to a negative number, my temperature has to be higher than 146 degrees Celsius. Questions, ladies and gentlemen, on that problem? Also, I can find delta G superscript 0. I can find the delta G standard. That's going to be analogous to the enthalpies of formation and enthalpy of entropy. And the delta change of entropy. I can apply Hess's law to delta G's as well. So literally speaking, if I give you delta G's and I give you the delta H's and the temperature, you can solve for the delta S for the reaction. If I give you the temperature, delta S, and the G, you can solve for the enthalpy, simply using Hess's law. Summation. If delta G is negative, the reaction in the forward direction is spontaneous. If delta G is at 0, the system is at equilibrium. If it's positive, the reaction is spontaneous, but in the reverse direction. If it's negative, forward reaction spontaneous. If delta G is 0, you are at equilibrium. If delta G is positive, you have a spontaneous reaction, but it's in the reverse direction. So let's talk about delta G at equilibrium. If we've got a delta G 0, the system's at equilibrium. So it must be equal to the equilibrium constant. Standard free energy is directly linked to the equilibrium constant by delta G is equal to negative RT ln of K. Jenna, if my K value is bigger than 1, is my reaction spontaneous in the forward direction?
Yes. I think.
Say it a little more positively, Jenna.
Yes.
Very good. If K is bigger than 1, then the ln of K is a positive number. If the ln of K is a positive number, that means this term minus RT times the ln of K is going to be negative. My delta G is going to be spontaneous. Similarly, if my K equilibrium is less than 1, then the ln of K is a negative number, and negative times a negative leads to a positive delta G. It is not spontaneous in that direction. I've gone through all this just in a second. This is in the way. There we go. So if I'm looking to relate my equilibrium constant with delta H and delta S, I plug my delta G equals negative RT ln K into the formula above. And I get delta H minus T delta S is equal to negative RT times the ln of K. I divide both sides by negative RT, and I get S over R minus delta H over R times 1 over T is equal to my ln of K. Again, as we have done in every chapter so far, we have developed an equation. We've developed an equation that develops into an equation of a line. If I plot the ln of K, which I can measure, versus 1 over T, I will get a straight line. The slope of that straight line is negative delta H over R, and the y-intercept is going to be equal to S divided by R. So when I have this, this equation of my line, if I'm plotting ln of K versus 1 over T, my negative delta HR is going to be the slope. My delta S over R is going to be the y-intercept. The slope of a graph of ln K and 1 over T is 6,092.2. The y-intercept is 27.136. Natalie, what is my delta H value? What do I equate delta H with? Delta H divided by R. What's delta H divided by R?
Delta H divided by R. I don't know.
Look at the slide. I don't know. It's a perfectly good answer. Parker, you got your volume fixed yet?
Can you hear me now?
Yes, I can.
All right.
Parker,
Is it the slope?
All I got to do is find out what my slope is, and my slope is equal to negative delta HR. So if my slope is 6,092.2, all I have to do is multiply the 6,092.2 by R, and that will give me my delta
Great.
H. So I multiply the 6,092 by 8.31 joules per mole K. That gives me 50,610 joules per mole, or 50.61 kilojoules per mole. Ethan,
Yes.
my y-intercept is 27.136. What's the value of my delta S? Look on the slide.
Wait. Okay. So the delta. Wait. Delta H R. The delta. 20. So let's see. 27.136 divided by.
Not divided by. S divided by R equals the y-intercept.
Oh, 8 point. Okay, so times 8.31 then. Okay, 225.5.
But that again, yeah, 226 joules.
Or yeah, basically, yeah.
So my y-intercept is equal to a positive delta S over R. So I just multiply my R value, my 8.31, by my y-intercept. That will give me my delta S.
And I guess for the delta H, so that's for this slope. So negative 609.2 times 8.31 gives us, well, I guess like 5.
But remember, that's, Ethan, it's 50,000 and something.
Yeah.
But you multiplied it by 8.31, which is joules.
Oh, okay. I need to convert the 8.31 to
Either
like
that or you
kilojoules.
just wait till the end and divide by 1,000. Okay, Ethan?
Okay. I guess either way that gives us 50.6. I got 50.62, but I guess it's a 50.61 on the.
Close enough. Okay. Just like the Clausius-Clapeyron, if I have 2 points, I can solve for the other one of either temperature or K. I can also solve for delta H. The overall reaction, if I have my first one equal to that first value and my second one equal to the second value, my S divided by R's go away. And what I end up with is an overall, for the 2-point equation, ln of K1 divided by K2 is equal to negative delta H divided by R times 1 over T1 minus 1 over T2. Enthalpy for a reaction is negative 25.8. At 298, my equilibrium constant is 1,400. What is the equilibrium constant at 655 K? I've got my reaction. I'm asking for one equilibrium constant. I have both T's and I have delta H. Plug in the values. The ln of my one equilibrium constant divided by my second one is equal to a negative, my delta H is a negative 25.8. We have to remember delta H's are in kilograms, kilojoules, R is in joules. So I have to divide my 8.314 by 1,000. I multiply this by 1 over the temperature of the first equilibrium constant minus 1 over the second one. I solve the right hand of the equation. I get a positive 5.68. I need to get rid of the ln, so I raise that to the e to that power is equal to just what the ln value was. E to 5.68 is equal to 293 times K2. 4.8 is equal to K2. Questions, ladies and gentlemen? Questions? Thank you for shaking your head, Jenna. At 150 Kelvin, the K value is 1.4 e to the negative 6. While at 175 K, the K value is 4.6 e to the minus 4th. I want to know delta H, delta G, and S, delta S. Do I have a way of getting delta H?
Yes.
Who answered yes?
Jana, me.
Jana? Okay, good. How am I going to get delta H, Jana?
We can put an X, we can start setting up the equation of ln k1 over k2 as normal, but for h to the h of the delta H of the reaction, we could put X instead.
Absolutely. I know this is my formula. ln K1 over K2 is equal to negative delta H reaction divided by R times 1 over T1 minus 1 over T2. I know what T1, T2, K1, K2 are. I know what R value is. I'm going to plug everything in. And I am going to solve for delta H. K1 over K2 ends up being the ln of 0.00304. Negative delta H. Negative delta H over R is equal to, or multiplied by 1 over T1 minus 1 over T2. I do the left-hand side of the equation, and that ends up being 0.00798. I divide 5.79 by 0.00798, and I end up with 50,200, which I then change to kilojoules per mole. I now have my delta H. Can anybody suggest how I get from delta H to delta S? How do we get from delta H to delta S? I'm getting a whole lot of crickets out there, guys. Remember, the 1 point expression is the ln of K is equal to negative delta H over R times 1 over the temperature plus S0 over R.
So then wouldn't we be able to just input all the values again of K1 or K2, and then we would be able to find the S for those?
Absolutely. All I'm going to have to do, I've got my value of H0. I can do a couple things. For my delta G, I know that delta G is equal to negative RT, the ln of K. I can plug in R, the K value, and my T value. That will give me my delta G0. I can plug it into delta H minus T delta 0 to end up with my S. Or as you suggested, I can take my ln of K, make that equal to negative delta H over R times 1 over T plus S0R. Again, we have two ways of doing this. All I got to do at this point is take one of my K values and the temperature. And plug it into my equation. So I can plug it in to that original equation, or I could find what the delta G is and then plug that into the delta H minus T delta S. Questions, ladies and gentlemen? Questions? Do you need to take a break for a second? I need to take a break for a second. I'll be back in 5. Anybody out there? Jenny, are you getting this? Does this make sense? Ethan? Ethan, you doing okay with this?
Yeah, I'm doing all right with this.
Jana? Good. I'm sorry. Good. Jana, you doing okay with this? You're going to have to manipulate between one and the other of these equations. There will be one of these type problems for sure on the test. For sure. Any questions? Anything? Guys, I'm here. This is the time to ask. What are you not getting? Jordan, you good? Jordan?
I think so. It's just a little hard to follow with like the screen being a little behind, but I'll just go back and rewatch it.
Okay. Leonardo, we doing okay?
Yeah, I'm good.
Ethar?
Yes, I'm good.
Manuel, are you doing okay with this?
Yeah, doing great.
All right. Again, manipulating these equations. If I find delta G is negative 177 kilojoules per mole, if I want to find K at 25 degrees Celsius, very easy. All I got to do is take my delta G, divide it by RT, negative RT, and take the inverse log of that. In this particular case, what I did was I converted kilojoules to joules by multiplying by 1,000 joules per kilojoule and divided that by 8.314 multiplied by the temperature. That number turns out to be a huge sucking number. Ends up being the log of ln of 734. And when I get K being equal to E raised to the 734, that number turns out to be 106 times 10 to the 31st. New problem. My equilibrium constant is 7 times 10 to the minus 84th at 25 Celsius. What is delta G? I simply take the ln of my equilibrium constant, multiply that by 8.31 times 298, and that's going to get me my value. Straightforward plugging question. 10 more slides, guys. Now, we've been talking up to this point. We have been talking about delta G under standard conditions. All of the molarities are 1 molar, and we're dealing with 25 degrees Celsius. Now, if I'm using non-standard conditions, I need to use delta G versus delta G superscript 0. And delta G is going to be equal to delta G superscript 0 plus RT times the ln of Q. And we have to remember that Q is nothing more than the equilibrium expression. At equilibrium, delta G is equal to 0. Away from equilibrium, that delta G is going to tell you which way the reaction goes spontaneously. So I have an equilibrium constant for the reaction. That is 1.33 at 298. My standard delta G is 5.4. If my initial pressure of N2O4 is 0.453 and NO2 is 0.122, calculate delta G and predict the direction the reaction will proceed spontaneously. So I'm working with delta G is equal to delta G superscript 0 plus RT ln of Q. Natalie, do you remember what Q is? Again, guys, turn your screens on. Vanessa. Vanessa,
Yes.
do you know what Q is for this reaction?
Q for this reaction.
This reaction, N2O4 in equilibrium with 2 NO2s.
Could you help me work through it?
Absolutely. Thank you very much for asking. All right. An equilibrium expression
Okay.
is the concentration of the products raised to the coefficients divided by the concentration of the reactants raised to their coefficients. Is this somewhat striking a memory, Vanessa?
Yes, somewhat.
Okay. Concentration of my what's my product here?
Your product would be 2NO2.
Okay. Do you have the pressure of the NO2?
Yes, it's 0.122 ATM.
So what am I going to have to raise? What power am I going to have to raise to 0.122 to?
To 2.
I'm going to have to square it.
Okay.
All right, Vanessa, what am I going to divide that by?
Are you going to divide it by the 0.453?
Absolutely. 100%. So I'm going to take my 0.122 squared, divide it by 0.453. That number is going to be 0.0329. The problem gave me my standard delta G as a positive 5.4. So I'm going to plug that 5.4 into my delta G. To that, I'm going to add my R value in kilojoules multiplied by 298, which is the temperature in K for this reaction. I do all this math out, and I end up with a value of a negative 3.1. Negative value for delta G means that it is spontaneous in the forward direction. Questions, ladies and gentlemen, about this?
So there's usually no situation where delta G would be positive and spontaneous.
It's entirely possible. It depends upon Q.
Okay.
Remember? Do you remember, Manuel?
Yep.
If Q is greater than K, if Q is greater than K, then you are going to get a reaction that goes towards the reactants, correct?
Yep.
So if Q is big enough, remember, okay, let's think about this. What we're doing for delta G is we're taking RT times the ln of K, correct, Manuel?
Yeah.
So if Q is less than K, delta G is going to be negative, proceeds in the forward direction.
Towards equilibrium, because
Towards equilibrium. Let me add another slide here, okay? Okay, delta G is equal to delta G0 plus RT ln Q, right?
Mm-hmm.
But remember, delta G0 is equal to RT times the ln of K plus RT times the ln of Q, right?
Mm-hmm.
So if Q is bigger than K, then I'm going to get, Q is bigger than K. I have to sit here. I am going to get a positive. I'm going to get a positive number here. And if I get a positive number, that means that the reaction is spontaneous in the reverse direction. If K is bigger than Q, then I get a spontaneous reaction in the forward direction. That's all this is saying right here.
I
And
got
it's
you.
something
Okay.
we already knew from dealing with K's and Q's when we're in the equilibrium chapter. New problem, we don't have that many more of them, guys. Consider the equilibrium reaction. I2 plus Cl2 in equilibrium with 2 ICLs. My Kp at 25 degrees Celsius is 81.4. Calculate delta G under standard conditions at equilibrium and with the individual pressures being what they are. One of these you can answer right away. No calculations. What did we say delta G was equal to under equilibrium?
K.
Nope.
It's 0.
Delta G at equilibrium is 0. So you know that answer right off the bat. Delta G, standard conditions, is equal to negative RT times K. Do I have a K value? Do I have a K, ladies and gentlemen?
You do.
Do I have a temperature?
Yes.
So can I figure out delta G is equal to negative RT times the ln of K?
You can.
I do that. My delta G under standard conditions is a negative 10.9 kilojoules. Keanu, is this spontaneous in the forward direction? Keanu. Natalie, is this spontaneous in the forward direction? Guys, I need to see your faces. Everybody put on, thank you, Vanessa. Satari, Natalie.
I'm on my phone, so I'm sorry. That's
No,
on me.
no problem. That's understood, Manuel. I know you're here. These other people, I'm not entirely certain.
It is spontaneous, by the way, in the forward reaction because it's
Thank you
negative,
very
so-
much, Manuel. Absolutely. Spontaneous in the forward direction. So we've got the first answer. Second one, by definition, delta G at equilibrium is 0. The third reaction. I know that delta G of my reaction under non-standard conditions is equal to my delta G plus RT, the ln of Q. I know what my standard conditions are. I know what R is. I know what T is. And I know that my Q is equal to, in this particular reaction, I've been given my pressures. I know that my ICL is 2.55 squared divided by 0.325 divided by 0.221. So I've got my Q value is 90.5. I plug everything in and I get my delta G is equal to a positive 3 kJ. Under these conditions, is it positive in the forward, is it spontaneous in the forward direction or the reverse direction?
The reverse.
Reverse direction. Now let's look back at the original problem. K was 81.4. My Q was 90.1. What's bigger, Q or K?
Q.
So remember back in equilibrium, we said when Q was greater than K, we get a movement towards the reactants, which is exactly what this is predicting. So we gave you the answer in equilibrium. We're giving you the Y now. Does this make sense, guys? I need a suggestion. I want to know delta G at 25C. What is the first thing I'm going to do in this problem? By the way, this is the last problem in this chapter. What am I going to do here, guys?
You would do the 204.9 times, I mean, negative 204.9 times 2 minus
ahead. Oh, great.
negative 394.4 times 1. And then add negative 62.3 times 1.
We're going to use absolutely. When you're ahead, stop talking.
Okay.
Is that Vanessa?
It's Natalie.
Natalie, but Natalie, when you're ahead, stop talking. You gave me the exact answer I wanted. We're going to find our delta G of the reaction, delta G standard reaction, by using Hess's law, because we have the delta G's of each one of our substances. We're going to take the negative 204.9, multiply it by 2. From that, we're going to subtract a negative 394.4, and we're going to subtract a negative 62.3. We end up doing that. My delta G is a positive 46.9 kilojoules. I'm going to plug that into my value of delta G0 plus RT ln Q. My values are For the COCl2, 0.744, I'm going to square that because there's the coefficient of 2. I'm going to divide that by the pressure of the CO2, which is 0.112, times the pressure of the carbon tetrachloride, which is 0.174. I do that, I get my Q is equal to 28.4. So my delta G of reaction is 46.9 plus my R times my temperature in Kelvin times the ln of what my Q is. This ends up being a G of reaction of 55.2. Vanessa, are you driving? Guys, that's the end of this chapter. Any questions? I got 20 minutes here. Any questions, ladies and gentlemen? Okay, let's take a breath then. We're going to take a breath, and as I get on to, no, I don't want to do that. I want to get out of this. Okay. We're going on to electrochemistry. Questions about the last chapter? It is probably one of the hardest chapters you will ever do in any subject. Thermochemistry is one of the most insidious things to have to deal with. Are we good? I'm hearing a lot of crickets out there, guys. Go
I
ahead.
think I'm good.
Yes, Professor.
Go ahead. Thank you, Ethan. Somebody was just talking.
No, I was saying I'm good.
Okay, Anaya. All right. Are you seeing the electrochemistry slide?
Yes.
All right. I'm going to hopefully get through balancing redox reactions, but I'm going to do it very quickly, and that is where we're going to begin on Thursday. We got a lot to do in this chapter, but it makes a lot of sense and it's fairly simple. We're going to begin by assigning oxidation numbers, balancing redox reactions. Then we're going to talk about electrochemical cells, batteries. Very important because most of your lives depend upon batteries now. We're going to deal with electrochemical cell notation, standard electrode potentials. We're going to deal with the activity series. When you were dealing with single replacement reactions, we just gave you this activity series and said, on faith, just know that this is true. Now you're going to get to know the why that this is true. We're going to deal with Gibbs free energy and cell potential and the relationship of cell potential and equilibrium constant. We're going to deal with the Nernst equation and concentration cells. So when we're dealing with electrochemical reactions, we have to realize that what is happening is we are getting electrons transferred from one thing to another. When that happens, we need to keep track. We need to keep track of the electrons and where they're going. And in order to do this, what we do is we assign something called oxidation numbers. And there are some rules we're going to need to apply for this. An oxidation number is the charge on the specific atom within the molecule. That's all an oxidation number is. Rules. Elements in their elemental form have an oxidation number of 0. So silver, magnesium, O2, Cl2, all have oxidation numbers of 0. If you have an ionic compound, the oxidation number of a monoatomic ion is the same as its charge. So if I have NaBr, the sodium's oxidation number is a 1 plus, Br's is a 1 minus. If I have FeCl3, iron's oxidation number is a +3, chloride's is a -1. Making sense so far, guys? Come on, guys. I've asked you, I have asked you all to put your visuals on. Vanessa, I know you're in the car. Don't worry about it. Put your visuals up. I want to see you. Do not. Could be. Ethar, are you here?
Yes.
Jordan, you here?
Yes.
Vanessa, I see you in the car. Natalia.
here.
Natalia.
I am here.
Benita.
I'm here.
Jenna.
Here.
Jennifer. Manuel.
Here.
Parker.
I'm here.
Araceli.
Here.
Nicole. Not here. Jessica. Jessica.
Here.
Thank you. Keanu. Natalie.
I'm here.
Jana.
Here.
Leonardo.
Here.
Anaya.
Here.
Natalie. Natalie.
Here.
Satori.
Here.
Raylena. Raylena. Ria.
Here.
Emily.
Here.
Ethan. Ethan.
Here.
Okay. Now, Vanessa has dispensation. She's driving somewhere. If you do not have dispensation, turn your videos on or that check mark just gets turned into an A. Parker, Keanu, Manuel.
Bro,
Manuel,
I'll turn my camera on.
That's
Go
fine,
ahead.
Manuel. Manuel, I understand.
I'm
Keanu
also on my
Parker.
phone and my service is not good enough for the camera right now. I'm outside.
Okay. Jana. Thank you. Thank you, ladies and gentlemen. Okay, oxidation numbers. Elemental form, 0. If you have a monoatomic ion, the oxidation number is the same as the charge. If I have Fe2O3, the iron is a +3, the oxygen is a -2. Non-metals are going to have a tendency to have negative oxidation numbers. although some are positive in certain compounds or ions. Oxygen will always have an oxidation number of -2, except when it's in the peroxide ion, when it has an oxidation number of -1. Peroxide ion, oxygen is bonded directly to another oxygen. Hydrogen is a -1 when it's bonded to a metal. It is a +1 when it's bonded to a non-metal. So in the compound lithium aluminum hydride, if we look at the AlH4 minus ion, the H in that particular ion, because it's bonded to a metal, is a -1. On the other hand, if I have HCl, the H is bonded to a non-metal, the H is a +1. Non-metals, when they're bonded with a more electronegative element, may be positive. So if I have the ion ClO4 minus, the oxygen will be a -2. So you have to ask yourself, what number when bonded with 4 -2 oxygens equals a -1? What number plus a -8 equals a negative, well, I'm sorry, excuse me. Yeah, what number plus a -8 equals -1? Ethan?
+7
+7.
or +7. Yeah.
Emily? If oxygen is a -2 and IO3 is a -1, 2 times -2 is a -6. What number plus a -6 equals a -1?
5.
+5. Sum of oxidation numbers in a neutral molecule is 0. So if that's the case, my molecule, K3PO4, we've already said monoatomic ions have their charge. So each one of the potassiums has a +1 charge. The PO4 is a -3. -3 plus 3 plus 1s, the total for the molecule is 0. The sum of the oxidation numbers in a polyatomic ion is the charge on the ion. SO4 2- has a 2- charge. Each oxygen has a 2-. There are 4 of them for a total of 8 minuses. What plus a -8 equals -2? Rhea. What plus a -8 equals -2?
What?
10.
Nope. What number plus a -8 equals -2? What do you have to add to -8 to get a -2?
-6.
+6. +6, ladies and gentlemen. So if I'm looking at that, let's look at PO4 3-. What's the charge on the oxygen? How many oxygen atoms do I have?
4.
4. Each one is a -2, so what's the charge on the oxygen? There are 4 of them. Each one's -2. What's the contribution from oxygen?
-8.
-8. So what plus a -8 equals a -3?
5.
+5. So the oxygen number for phosphorus in PO4 3-, it's going to be a +5. KCl, neutral molecule, both monoatomics. Potassium's a +1, chloride's a -1. Total charge is 0. Let's look at iron carbonate. Jenna, do you know what the charge on the CO3 is?
Is it just a -1? Oh, sorry.
-2, okay? So if CO3 is a -2, what's the charge on the Fe?
A +2.
+2. So the oxidation number for iron is a +2. Now, the CO3 has a -2 charge. Jenna, what's the contribution from oxygen?
-6.
-6. So Jana, what plus a -6 equals a -2?
+4.
+4. That is the oxidation number for my carbon. NH4 taken twice, Cr2O7. Chromate is a -2. Because there are two ammonias, the NH4 must be a +1. Let's deal with the ammonia +1 first. H's bonded to nonmetals are always a +1. How many H's are there in NH4? Jessica? NH4. How many hydrogens?
There's 4 hydrogens.
4 hydrogens. H is bonded to a nonmetal, so it's a +1. What's the charge contributed by the hydrogens?
5.
What?
I'm sorry.
Each hydrogen's a +1, and there are 4 of them. So what's the total charge on the contributed by the hydrogens?
It's 5.
How many hydrogens are there?
4, sorry.
Each one's a +1.
Mhm.
So what's the total charge contributed by the hydrogens?
4.
4.
Sorry.
So you got to ask yourself, what plus a +4 equals a +1?
-3.
-3. That is the charge on the nitrogens.
Okay.
Now we got to deal with the dichromate. The total charge on the dichromate is a 2-. Ethan?
Yeah.
Cr2O7 equals a -2 charge. What's the contribution from the oxygens?
Okay, well, the oxygens, wait, let's,
How many of them are there?
so, wait, there are 7 oxygens, so -14.
So -14. So what plus a -14 equals a -2?
+12.
But that +12 is distributed amongst how many chromiums?
2.
So I have to divide the +12 by 2 so that each chromium has an oxidation number of a +6. Does that make sense, Ethan?
Yes.
KMnO4. Last one we're going to do. Jenna. I'm losing this here.
O4
Thank
has,
you.
so it's
Okay,
negative.
first of all, split the ion up.
Okay.
MnO4. What's potassium's charge?
+1.
So if potassium is a +1, then what does the charge of the MnO4 have to be?
A -1.
So we've got the oxidation number of potassium as a +1. Okay. Now, how many oxygens do you have?
4.
What's the charge contribution? What's the charge contribution from the oxygens?
-2, but then it would be -8 with the 4.
-8. 4 times a -2 is a -8. So what plus a -8 equals a -1?
+7.
+7.
Mhm.
Okay.
Mhm.
Okay, ladies and gentlemen, we are going to talk about oxidation reductions first thing on Thursday. Then we're going to get into redox balancing. Then we're going to get into the electrochemical cells. Any questions about what we've done so far today? We've gone through the complicated equations of the entropy and Gibbs free energy. Anything going on, guys? All right. Please keep your videos on. Believe it or not, I can see your expressions and I can see whether or not you're understanding something. Please leave them on. Down to 3 more lectures, guys. Finest kind, we're almost through this. Before I go, any questions?
I do.
Just one announcement. Those of you that have my face-to-face lab this afternoon, remember, we're not meeting. You're just meeting with your partner to discuss the presentation. I'm done with announcements. Who had a question?
I did, but it's about the test on the 20th.
Okay. Do you want to talk after everybody leaves, Jana?
Yeah, that's fine.
Okay. Guys, that's all for today. Bye, Jana. Bye, Ethan. Bye, Jessica.
Hey.
Natalia.
Bye. Thank you.
Professor, I have a question about the lab.
Leonardo, yes.
For the conversion of NaOH moles to H3PO4 moles, is it 1-to-1?
Are you talking NaOH or are you talking OH to H plus?
NaOH.
It's going to be a
It says
3-to-1.
1-to-1?
3-to-1.
Oh, 3-to-1. Okay.
But wait a second, Leonardo. Are you talking about in your split when you're going up the rise?
Well, on the equation, it just says like H3PO4 plus OH minus goes to H2PO4 plus.
That's why I needed to pin you down. It's a 1-to-1 relationship because you're only pulling one of those hydrogens off of the phosphoric acid.
Okay.
So when you do that, Leonardo, you're going to be able to get the concentration of your H2PO4, right?
Yeah.
So when you get that concentration, since it's a 1-to-1 relationship with the H3PO4, that's going to give you the concentration of your phosphate. Does that make sense, Leonardo?
Yeah.
Anything more?
No, that's all for me. Thanks.
Okay, Sachari, Natalie, anything?
No, that's all. Bye, Professor.
Bye, see you later.
I have a
Vanessa?
question.
Yeah, Vanessa.
When are you going to insert the grades for the homework of the lecture?
At the very end.
Okay.
Vanessa, what happens is I just go through everything at the very end. I don't do anything in the meantime. I add up everything after the entire homework has been submitted.
Okay.
It will be there before you take your final.
Got it.
I don't even know when I don't know what the date is that I've cut the cutoff date for the homework, Vanessa. Off the top of my head, I don't remember what it is, but I can't do anything until I reach that cutoff date. Does that make sense?
Yeah, I was just asking because without it, the grade, like I want to know what my actual grade is, you know?
Again, basically take what you're doing. If you want to figure out your grade, figure out how many of the questions you've answered. If you have answered 75% of them, then half of the homework grade is going to be 75% of that point value. Again, I don't have these numbers committed. Say the homework's worth 100 points. 50 of it is due to quantity, 50 of it is quality. So of that, if the homework is worth 100 points, then 50 points of that is going to be quantity, 50 points is going to be quality. I then am going to look up and see how many assignments you've done versus the total assignments. If you have done 75% of them, then 75% of the 50 or 38 points are going to be entered in to the homework. If you have answered, say 50% of the questions right, then 50% of 50 or 25 is going to be the number entered for your quality. At that point, I have 25 plus 38. 25 is the number you get right out of, it's your quality, 25 out of 50. And you did 38, so 38 divided by out of 50. I add those two numbers together and you would get a 63 out of 100 for the homework grade. Do you understand, Vanessa?
Okay.
Believe it or not, it helps you. It does help you. Keanu, are you there or are you?
Yes, I'm here.
Okay, I marked you absent because you're not staying in the meeting. You're going off somewhere. You didn't answer attendance when I gave it.
Sorry about that. That was my fault.
Okay, do you need to ask me a question, Keanu?
No, I don't have any questions.
Okay. Jana wanted to ask me something out of the presence of anybody else. So please, please depart now. Thank you. Okay, Jana, what did you have to ask?
Yeah,
I take it you're not going to be there on the 20th.
Yeah, so it's just in the morning. I'm going to be busy because of we have a religious holiday on that day. And so in the mornings there are from about like 7 o'clock in the morning
Okay. Well,
to about like 12
tell
or
me.
1 p.m. There's going to be like a prayers and stuff like that.
Okay.
So
I'm willing to work with you, Jana. What are you requesting?
Okay. I wouldn't want to postpone it in any way since like we have the final on like 2 days later. So I would think if you would just extend the time to be like till midnight
No,
of that
no, that's not going to happen. I've got too much happening, Jana. And to be honest with you, Jana, it was a mistake when I did it the last time. It was a mistake because there's too easy a chance for somebody early on to get the questions and to tell somebody about it. So I'm sorry, but no.
Okay.
I will be
All right,
reasonable. I
I
will
guess
be
I'll just-
reasonable about it, but midnight is not an option.
Okay.
When can you get it done?
Um,
I'm trying to work with you, Jana, but midnight is not going to work.
I'm honestly not sure.
Okay, what time is the religious?
I guess
What time is it over, Jana?
I would assume usually it just extends to like 1 p.m. 2 p.m. So maybe and the place is like right by HCC, so it's about like an hour away from my house. So
if I extend you to 6 p.m.,
I would say if you could give me to like 6 or 7,
I will do that.
6 or 7 p.m. would be good.
I will go ahead and do that. That's reasonable. Is that not reasonable, Jana?
It is. It's pretty good, and you make a very good point.
We're okay. I'm gonna have to get in there and do this. Okay, I will do this as soon as I get off. I will make it till 7 p.m. Okay, Jana?
All right. Thank you so much.
You're welcome. Have a good day.
All right. Thank you so much. Have a great one. You too. Bye-bye.
Bye.